Hello, thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. It is great to have your company. We've got a lot to talk about today, as always. A bit of sad news to start with the passing of Dr. Frank Drake. We'll also be focused on the DART mission. This is a really exciting mission and it's not far away, only a few weeks. And the first image of an exoplanet taken by the James Webb Space Telescope. We'll be talking about that and answering audience questions about the observable cosmic microwave background radiation and planets orbiting stars, orbiting black holes. Can it happen and what would it be like? Stretchy, I imagine. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us as he does week in, week out, month in, month out, year in, year out, not quite a decade yet, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Yes, it'll be decades soon, won't it?
It will.
if we last that long, yeah.
Oh, gosh, I hope so.
Yeah, so do I. Yeah, it's going to be 7 years by the time we get to the end of this year. It's phenomenal.
I've said it before, but I didn't think it would last.
No.
We've lasted longer than the average marriage.
Yes, that's a very good point. We have.
See, that's my wedding ring.
Yes.
And that's my Space Nuts ring.
There you go. So you're tied to Space Nuts. They're not. Have we got a prenuptial agreement?
I don't know. This is probably one of the only business arrangements that's still done on a handshake.
Not even that.
Not even that.
No.
Not even that. No. How have you been, Fred?
Yes, I've been well, thank you.
That's good.
Good. It's happening here, but it's all exciting.
Well, I've had a fun week.
Yeah, that's what I hear.
I spent some time in hospital, routine stuff. My son's in hospital, my dad's going to hospital, and my computer died and my email inbox wiped itself and I lost everything in separate incidents. So can't retrieve anything, and that's where a lot of the Space Nuts questions were. So early appeal for questions because I've lost the lot. Shouldn't keep them in my inbox. But that said, my inbox shouldn't wipe itself,
No, it shouldn't. You probably need grievance counselling for that loss. Because
I feel like I do.
I'd feel like that too if I lost mine.
What's stupid? I can't remember what was in it.
Well, there you go.
But I shouldn't have to because it should be there.
Indeed.
Anyway, it's been a harrowing week, but I've got a new computer down by my ankle, which is doing a sterling job and will probably last me a couple of months. So that'll be good. Now, Fred, let's talk about these stories, incidents and accidents, and very sad story to start off with, the passing of astrophysicist Dr. Frank Drake at the age of 92.
Yeah, it's a good innings, but we've sort of got used to Frank just being there.
Yeah.
He, as you said, 92 years old. He was born 28th of May 1930 and sadly died on the 2nd of September this year, peacefully and from natural causes. He, of course, is famous for his work with SETI, the Search for Extraterrestrial Intelligence. And we have talked many times about the Drake equation itself, the equation he postulated in 1961. If I remember rightly, it was a small conference or workshop of people who were interested in the possibility of some sort of communication with extraterrestrial civilizations, perhaps even detecting radio signals or something like that. That workshop included, Carl Sagan was one of the people there. And I think they came up with a sort of false name for themselves because they were all scientists, but the idea of, talking about extraterrestrial life was so unfashionable in 1961 that they felt they would have been drummed out of the profession. So they called themselves something else. I can't remember what it was. But never mind.
I know, SETI and Forgetty.
You've probably had that one saved up, haven't you? It's a good
Just thought of it now.
It's very, very good. Yes, you should be on the radio, Andrew.
I'll try that one day. Yeah.
So, the whole idea of the Drake equation was sort of get people thinking in this group of scientists, get them thinking about what the issues are in terms of trying to understand what possibility there is of us picking up signals from extraterrestrial civilizations, because he actually basically made observations to try and detect them, quite well-known ones with large radio telescopes, because he was an astrophysicist. But the Drake equation itself, it's probably just worth briefly going through it, Andrew, because,
Yes.
so entrenched in our thinking on astrobiology, excuse me, the morning frog in the throat there, so entrenched in our thinking that we don't really pay that much attention to its details. We just know about it. So the equation is several parameters multiplied together. And excuse my ropey throat there. It's quite often the case during the morning. So I'll do my best to speak properly rather than be coughing into the microphone all the time. So you start off, the thing you're trying to work out is the number of detectable civilizations in our galaxy. That's the thing that these 7 parameters all essentially multiplied together will give you an estimate of. And so it starts off with the rate of star formation, which is something even back in 1961, astronomers knew reasonably well. Roughly 30 stars per year within our galaxy are being born. And so then you multiply it by a series of fractions, the fraction of stars that have planets. Now, they had no idea what that was in 1961. And I think, there was a bit of a wild guess that it might be 1 in 10. But we now know, and it's the one thing that we do know with much more certainty than we did back then, that most planets have stars. In fact, it's possible that most stars have planets.
We knew what you meant.
Yes, it's possible that all stars have planets.
You know why you got that wrong? Because you had a throat in your frog.
An Alphagetti and SETI as well. Yes. So you multiply the rate of star formation by the fraction of stars that have planets, which we now know is probably 1, effectively, then the number of habitable planets in each planetary system. So you might think about planets in the Goldilocks zone. We know that there's a good chance that there might be living organisms outside the Goldilocks zone. You've only to think of the possibility of the oceans of Europa, the oceans of Enceladus, which are way, way outside the sun's Goldilocks zone. Yeah. So you might think that number could be quite high, because if you've got a solar system with several planets in it, and we've got 8 in ours, so we think ours might be fairly typical, then you're going to find at least one probably that's in within the habitable zone. So the number of habitable planets per planetary system, you can probably put at something near 1. But then you've got the big unknowns, the fraction of planets on which life occurs. And that's a total, we can only guess at that. Yeah. My guess is that microbial life will kick off wherever the conditions are right for it to do so. Yeah. Temperature, pressures, the right kind of molecular background, lots of organic chemicals, enough lipids that you can form cell membranes, all of those things that feed into that. And so it may well be that fraction is reasonably high. If you've got a habitable planet, that you might, that it might actually host life. But then the next one is the really tricky one, the fraction of those life, or the fraction of life planets that kick off intelligence. Yeah. And, the jury is out on that. There are really 2 schools of thought. One says that evolution to intelligent life is inevitable if you've got the right conditions. Another says that it is likely to be so rare that we might be the only species in the galaxy. So take your choice with those. And then finally, the fraction of those intelligent civilizations that develops communication technologies. Because you can imagine, if there's intelligent life in the oceans of Europa or Enceladus, we're not going to know about it. No. Because they don't see the stars. And so that then it gets multiplied by the average length of time that a civilization lasts effectively. And that's another unknown. People guess 1,000 years or something like that. And so what you've got is you're looking for the number, and you're multiplying a rate at which stars are born by a time, and that gives you a number. Marvelous equation, very well thought out, and it stood the test of time.
It has. The answer is still 1.
It might well be. Yes, that's right. Us. Yes, indeed.
That's it. Yeah. I choose to believe that, we're probably the example of it, that if the conditions are right and the circumstances are right, the planet's in the right place, everything comes together right, life will exist. So when you think of the size of the universe and the number of planets that we're now starting to understand that are out there, there's got to be another one somewhere with some kind of life beyond microbial. I'm thinking maybe vegetation.
Yeah. Well, even that's a big step. That's
it is,
right.
but it's not as big a step as intelligent
No,
beings.
indeed.
But marine life, perhaps. Who knows? Krill. I keep going with krill.
You like your krill, don't you?
I do. I reckon that's what we'll find. But a great equation, great concept to come up with all those years ago.
Yes, and ahead of its time, if I can put it that way. But no, it's made him very famous, of course,
and rightly so. Yeah. But very sad to hear of his passing. But 92 is a damn fine knock in cricket circles.
Indeed, it is.
Yeah.
Yes.
His daughter said some beautiful things about him when she announced his passing as well.
Yep.
Now let's continue on, and we're headed for Dimorphos. This is the DART mission. Now, the DART mission is a very exciting proposal because they're going to smash something into a moonlet, as far as I understand. And that will be an experiment to see if Earth is ever threatened by an asteroid, aka Bruce Willis won't be around to help us. We can help ourselves by diverting it through a major impact like this. And it's set to happen, the 26th?
26th of September, yeah, that's right. And so you and I have talked about this before, and it is very exciting. I think it's going to, it will be really good to demonstrate that we can actually just shift an asteroid around a little bit if we need to. So the asteroid itself, the target, is called Dimorphos, which is a rock only about 170 meters across.
Yeah.
And that's what the DART spacecraft will hit, and that's short for Double Asteroid Redirection Test. It's an acronym, on the 26th. But Dimorphos is in orbit around its parent asteroid. So this is the moon of an asteroid. And that asteroid is called Didymos, which is a great name, which is much bigger. It's getting on for a kilometre. It's about 780 or 800 metres wide.
Yeah.
So there it is, Didymos with Dimorphos in orbit around it. And the idea is that the spacecraft will clobber the smaller one, Dimorphos, and change its orbit in such a way that we can actually detect that orbital change. And by changing its orbit, I mean its orbit around its parent asteroid rather than the orbit of the pair of them around the sun. And that's the really clever part of this experiment, Andrew, because if you just charged at an asteroid with a small spacecraft and gave it a ding, it would take probably long time, maybe years or possibly even decades to work out whether you've changed the orbit at all. Yeah. Whereas if you've got something that's going around smaller objects in a matter of hours, then the orbital change is easier to detect. And so the reason why the story's sort of in the news already, even though we're still a couple of weeks away from the impact, is that the latest news is that new observations have been made with ground-based telescopes, actually one in Arizona, one in Chile. The Magellan telescopes, I visited them on the mountain called Las Campanas in northern Chile. So those two telescopes have been used to observe the orbit of Dimorphos and actually calculate what it is now, because it's important to know that, to understand exactly how it's behaving. Since there are other factors that could come into this, like the possibility of solar radiation playing a role. You don't want, the radiation pressure that the asteroid feels from the sun, you don't want that to be screwing up your observations. So we now have a really good estimate of what the orbit's like before the impact. And of course, over time, it might not be too long. It might only be a few days. or a few weeks, we will know what the change has been to the orbit of Dimorphos. So
Yes.
really exciting stuff, and we will talk about this again soon, no doubt.
In fact, we may well have a reporter on the scene. One of our Space Nuts listeners, a very keen follower of Space Nuts, Marie-Claire Mercier, has actually got herself a ticket to the big day NASA is having at Cape Canaveral for the impact. So she'll be there, guns blazing, and we're hoping to get her on the program after that date to have a chat about what she witnessed and how it all went down. So really looking forward to that. Hope we can make that happen. And you lucky duck, Marie-Claire.
Yeah, but great to have. We get our own team of reporters out there. This is brilliant stuff.
So we're hurriedly sending her some Space Nuts stuff so she can wear it on the day.
Very good. Delighted to hear that.
Hopefully we'll be represented, but she's really keen to get on with us. So we'll try and make that happen.
Yeah.
But very excited to see how that particular experiment goes. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
All right. Fred, let's talk about the next story, and this is exciting too, and sort of to a small degree dovetails in with the Frank Drake equation, and that is that the James Webb Space Telescope has just sent back a picture of an exoplanet orbiting a distant star, which is something we talked about it doing. It was one of the main things that it was designed to do, and it has brought back the picture. Up until now, we've only seen artists' impressions of these worlds that have been discovered since the 90s, and now there are thousands of them and many, many more to be catalogued. This is the first time we've got a picky of one, isn't it? Or this first one for the James Webb Space Telescope anyway.
It is. It's the first with the James Webb Space Telescope because there are just a handful of exoplanets which have been imaged, and what you might call the flagship of those, perhaps the poster child or something like that, is a system which has 7 planets called HR 8799. Actually, I beg your pardon, 4 planets which have been imaged. I can't remember which facility they were imaged by, but they've been imaged so many times that we've now got movies of them orbiting around their host star. That takes a bit of beating.
Yes. I remember that now. Yeah,
that's right. So this isn't the first time it's been done, but it's the first time the Webb telescope has done it. And that's great because it demonstrates that the equipment that it carries on board in order to allow this process to take place is working and is doing, exactly what was expected. So the device that you have to use to block out the light of a parent star instrument actually is called a coronagraph, and it dates from the idea of trying to block out the sun so you can see the sun's corona, which is what you see during an eclipse, the outer atmosphere of the sun. So you block out the light of the star because the planet itself is shining by reflected light from the star and could be millions or billions of times fainter. In the old days, we don't do this now, but we can do it on Space Nuts. It used to be compared with trying to spot the glow of the cigarette of the lighthouse keeper walking around the catwalk of his lighthouse next to the light itself. It's very, a very inappropriate thing to talk about now, but that's what it was compared with. And it's a really good impression that you get, something just glowing faintly next to something very bright indeed. So the coronagraph blocks out the light of the star. You've got to do it carefully because you can, throw the baby out with the bathwater if you don't do it properly. You block out the light of the planet as well. And so what we've got from the Webb telescope is this lovely series of 4 images taken with both of Webb's major instruments, NIRCam, the near-infrared camera, and MIRI, the mid-infrared instrument, at wavelengths of 3, 4.44, 11.4, and 15.5 microns, which are sort of standard infrared filters that are used for this sort of thing. So the 3 and 4 micron wavelengths are within what we'd call the near infrared. The 11 and 15 are what we would call the mid infrared, which is that region where the wavelengths are getting longer. And we've got images from each of those of the planet. Now, what that means is those wavelengths are chosen so that they will show up basically the features in the planets that sort of the planet itself is emitting light that is affected by the elements in its atmosphere and the molecules. And it's essentially the tool that you can use to work out things like the temperature of the planet. And basically the answer to that is that the temperature at the top of the cloud tops, because it is a gas giant, it's several times the mass of Jupiter.
Yeah.
This planet, which by the way is HIP 65426b, the cloud
very hip.
Very hip, yeah. Hip, by the way, is Hipparchus. It was a survey satellite that surveyed things in the early 80s, an astrometric satellite measuring the positions of objects. Had a little bit to do with that back in the day. So the cloud tops of the planet are hotter than everybody thought, something like 1400 degrees Celsius.
Ooh.
And it's, the curious thing is that its diameter is similar to Jupiter, even though its mass is probably rather higher. So it may be a curious rocky world. Its distance from the star itself, HIP 65426, its distance is about 100 times the distance that we are from the sun. So it's, in fact, 92 times further from the star itself than we are from the sun.
Yeah.
Which is about 14 billion kilometers. So that is a long way. But that, of course, feeds into our capability to detect it. It's very nice that we've got something that's far enough away that you actually do have a chance of seeing it.
Do we know what kind of star it's orbiting?
I was trying to find that, actually. Yes, we do. I think it's a giant star. I suspect it is a hot star to keep the temperature of this world as high as that at 100,
over that distance,
100 astronomical
for sure.
units or 92 astronomical units away. Yeah.
Now, when you look at these images, sort of like most images you get over a distance, they're just fairly blobby looking things. Are astronomers and scientists able to get much detail out of those images? Are they able to learn more about what the planet's makeup is?
I think in the end they will. That what we will be unlikely to see is continents and things of that sort, because the planet itself is below the limit of resolution of the telescope. It's below the physical possibility of seeing any detail on it. It's just a point source.
Yeah.
And so the details that you can see, the blobs, in particular, there are, some of them have got little patches of light next to them, side lobes or blobs around them. They are probably artifacts. They're probably fringes, in fact, because the telescope is working close to its physical limit of detectability, what we call the diffraction limit.
Yep.
And these are remnants of phenomenon that are associated with that. So I think what we're seeing through the through the near infrared camera images, we're definitely seeing fringing from that. And the structure around the images from MIRI, the mid-infrared instrument, and I suspect that is also fringing that's caused by the interferometric process used to suppress the light of the star. I might be proved wrong on that, and I'm sure that as time goes on, we will start to see much more information from these. This is a first shot at it, and it's remarkable that we've got such good images in 4 wavebands of this planet. So I think this speaks of a very bright future for the James Webb Telescope. And in fact, the research group that's published this, and I had a look at the paper, and it's got about 100 authors, probably more. The research group thinks that the telescope's performing about 10 times better than they expected in this regard. So wonderful. I think we'll see some really quite spectacular results coming from the Webb in this.
Yeah. I also wonder if it will get a better image of an exoplanet that might be closer to us. Is that a possibility?
Yeah, I didn't mention this object's 385 light years away, so it is a long way off. I think it was probably chosen because it's a planet that's known to be a long way from its parent star, so you're giving yourself the best chance detecting it. But yes, you're right. When you get nearer, I still don't believe we'll be seeing details, continents and things of that sort. But I think the things that we will learn will be easier when we look at nearer objects. Definitely.
Yeah. It's very exciting. It just seems like every other day there's a new discovery or a new announcement from the James Webb Space Telescope team, and we shouldn't be surprised by that. It's a brand new toy, and they're really pushing it to its limit at the moment, and it's coming up trumps. It's really doing a fantastic job.
That's right. It's I think it's, and the great thing, Andrew, is that it's absolutely across the board. It's galaxies, it's planets, the distant universe, and that's exactly what we expected from the from the telescope when it was being planned.
Yeah. Well, no doubt we will have more to talk about in a very short period of time regarding the James Webb Space Telescope. By the way, if you want to check out the images, you'll find them on several websites, but theconversation.com is a really great website for seeing, reading about that story, but also looking at those images and many other things. It's a great website in general. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, it is that time of the week where we just sit back and do nothing.
Oh, is that it? Good. Well, I might make myself a
actually,
coffee.
No, that's what happens in all the other periods of time between when we start and finish this show. But time to answer some questions. And we've got one short question from John and one question in several parts from Candice. But they're all kind of interrelated. So, they're hillbilly questions, basically. But we will get to that in a moment.
I thought we were the hillbillies.
Very possible. Very possible. John is from Barnsley in the UK. Hi, Andrew and Fred. Thanks for the great podcast. I only discovered it a month back, which would be 6 months back now, because that's how long ago he probably sent us the question.
Sorry, John.
But I've been listening to every episode every night. He's catching up. Since you said you're running out of questions, well, I am now because they were all deleted.
Yes.
I have a couple for you I've struggled to find an answer to. Would measurements of the cosmic microwave background radiation look identical to any observer in any position in the universe? Love that question. Or would it look different based on the observer's position and their own observable universe? And would the universe have been infinite in size immediately after inflation? And would the curvature of space-time have been flat during inflation as we measure it to be now? Thanks again. Very interesting questions.
They're terrific questions, yeah. And I love the first one because it actually highlights exactly what the cosmic microwave background radiation is. So let's just recap. We are sitting here on Earth in a universe that's 13.8 billion years old. We can look back with our telescopes in time because that's what happens when you look out into space. The further away it is, the further back in time you're looking because of the finite speed of light. And eventually we look back so far that we see back to a time when the universe was not transparent. It was opaque and it was shining brilliantly with light. And that's essentially the universe which is still glowing because of the Big Bang itself. We think that was a time about 380,000 years after the Big Bang. So that's as far back as we're looking when we see the cosmic microwave background radiation. What we see, though, when we analyze it, and there have been 3 spacecraft that have worked on this and given us a very accurate map of the cosmic microwave background radiation because it covers the entire sky. That map shows very, very tiny fluctuations in temperature across it, little blobs of slightly warmer, little blobs of slightly cooler.
Yeah.
And it's by analysing what we call the spatial frequency of those, that it's the distribution of those blobs across the sky that we learn so much about the Big Bang itself and the conditions that prevailed at the time that the universe became transparent. So it's like a wall of radiation with these little dips and troughs superimposed on it, a level of about 1 in 10 to the 5th. They're tiny, really tiny. It took a long time before they could be detected, rather than just seeing a constant, basically stream of microwave radiation from every direction. And by the way, it's microwaves just because the universe has expanded by about 1,300 times since the light was emitted. So what was visible light to start with 13.8 billion years ago is now microwaves, which is just as well, because if it was visible light, it would be very bright indeed.
Yes,
all over the sky.
We'd be very different creatures, I imagine.
I think we'd have been frazzled, actually. I don't think we'd have made it at all.
Okay.
So John's question is absolutely on the money, because our view of that is a kind of optical illusion. We are seeing that radiation, and yes, it's going to look more or less the same everywhere, but the tiny little patches of hot and cold on it, which, by the way, come from sound waves oscillating through the early universe, it's what are called the baryonic acoustic oscillations. Those little blobs are going to look different if you're in a different place in the universe. Even though your view is being, you can still only see as far back as the cosmic microwave background radiation. You might be in a completely different bit of the universe, which is much bigger than that sphere that we can see.
Yeah.
So you will see a different pattern of temperatures, but the power spectrum, the characteristic of those glows will be the same, because it's all to do with the conditions in the Big Bang itself. So it's a really, really perceptive question, John. And by the way, John comes from a place not very far from where I grew up. Probably speak a bit like I do, with a bit of a Yorkshire accent. And then the other questions. So inflation increased the universe's diameter hugely, but we don't know whether it was infinite. All we know is it stretched the universe rapidly, super rapidly, 10 to the minus 33 of a second or something of that order, and it stretches by 10 to the 50 or something in that order. It's, we just can't get our heads around it.
Yeah.
But may well have made it infinite. And in fact, as John suggests, it may have flattened the geometry of the universe. So by a flat universe, you and I have spoken about this before, we don't mean a universe shaped like a tabletop. We mean a universe in which the laws of geometry that we have around us actually work. So parallel lines never meet and things of that sort.
Yeah. Well, yeah. So infinite, not as in never ending, but infinite as in
never ending.
Never ending.
So let's.
My brain just went, stop, Andrew. You don't know what you're saying.
Yeah, no. Well, actually, I get that feeling as well for me. Best way to think of it is just to imagine the universe was like the surface of a sphere, which is, it's infinite in the sense that you could keep on going forever.
That's what I was trying to say.
But that's right. But it's bounded. It's bounded. It's not unbounded. That's the thing.
Well, that's what a ring represents. Eternity. It's never ending. See,
never ends.
Infinite.
I thought it was just represented the fact that you can stick something on your finger where you remember it.
Well, that's probably the truth of it. Yes.
Yes. But I do like that. I do like that impression. Yeah.
Yes. So did that also cover the curvature of space-time as being flat during inflation?
Yes. Pay attention, Andrew.
Wasn't sure.
I think I said that.
I think you did.
Yeah, the flat universe. No, it's absolutely right. Curvature of space-time. And that sort of flies in the face of the model I've just put up with a ball. But you get the idea.
Yes, I do indeed.
I hope John does too.
I'm sure he does. Thank you, John. Let's move on to Alberta, Canada. Hi, Candice. Hello, Dr. Watson and Mr. Dunkley. Love the content of your podcast. Has it got content?
Yes, something like that.
Makes the mind wander and wonder. I know you get a lot of black hole questions. My questions are not about black holes directly, rather about what is around them. I understand the only way we are sure there is a black hole at the centre of our galaxy is because of the stars we can see that are racing around something that is invisible. Now, about those stars. Now, she's got 4 questions here. I'll ask question 1, but they'll all dovetail into each other. Could these stars have planets orbiting them, or would the speed that they are moving prevent them from having planets, or would the distortion of space caused by the black hole prevent anything from settling into an orbit, or would the gravity of the black hole have trumped the gravity of the stars and just pulled anything relatively small, leaving nothing left but the larger stars? That's question 1.
Okay. No, great questions. And It's correct. It's not the only way that we know there's a black hole at the centre of our galaxy, because now we've got an image of its event horizon with the Event Horizon Telescope. This question might have come in before we reported that a few months ago.
Possibly.
But yes, there's a whole swarm of stars which are orbiting around the black hole in the centre of our galaxy, and it's by observing those over the last 30 years or so that we know that there's something in the middle that has enough gravity to keep them bound in their orbits, but it's got to be compact, and the only thing it can be is a black hole. So when you think about those stars, they're not being pulled apart. They're not being spaghettified by the black hole. That will spaghettify things that get nearer to it. But these stars are in stable orbits. They are affected by the gravity of the black hole because they are subject to quite strong relativistic effects. That means that they behave, rather than under Newtonian dynamics, they behave under the dynamics of general relativity, which is all about space being distorted by mass. So there will be, but they are still intact, and that means that their own self-gravity is enough to hold them together. And it probably suggests that if they had planets, depending on the mass of the planets and where they were in orbit around the stars, they would hold on to them as well. There might well be times, when there's a tug of war between the gravitational pull of the black hole and the gravitational pull of the star. But I can imagine that the situation will be that the planets could be in stable orbits around the stars.
Okay, well, that leads us to the next part. Now that we've established that, if there were planets around these stars, would there be anything preventing life from existing on them? Maybe the radiation, maybe something along those lines?
That's right. So there certainly is radiation. You are near a very strong source of X-rays, which is the black hole itself.
Yeah.
So I think there'd be a good chance that those planets would be highly sterilized, and life might not have taken off. It's a very good point. I mean, the gravitational, if you didn't have the radiation, I suspect, and you just had a black hole, say an inactive black hole, a quiescent black hole that's not doing anything, not gobbling up anything around it, then it might allow living organisms to form. Of course, I should qualify this, Andrew, by the fact that there are organisms that cheerfully grab radiation.
Oh, yeah.
Is it Deinococcus, I think its name is, can withstand 3,000 times the lethal dose of gamma rays for humans. And it's cheerful. I think it's called Deinococcus. I did a cartoon of it in Space Warp, the book, and it's an extremophile. It's basically a microbe that loves extremes.
Yeah.
So it may well be that there could be radiation tolerant microbes or living organisms on these planets. So never say never.
Never, indeed. Which leads to the next part of the question, which I'll paraphrase. What would the night sky look like on these kinds of planets?
Yeah, well, you're in the middle of a cluster of stars, so it would be much more brilliance in the night sky than we have in ours in the sort of galactic suburbs. I think there'd be lots of stars. Black hole itself would be something that you'd only see with infrared or radio observations. It would be a lurking monster not very far away. The nearest stars are within the distances from the black hole are measured in trillions of kilometres. That's the same as the planet of HIP, whatever it was that we were talking about a few minutes ago, which is 14 trillion kilometres away, I think, is the distance. Actually, it probably wasn't that. It's probably something slightly less than that. But anyway, trillions of kilometres. So the black hole would be a looming presence there, I think.
I think it'd be a spectacular sky.
Yeah, you'd still see, you're immersed in the galactic bulge, so there wouldn't be a Milky Way. You'd have stars all around you. You'd have a very, very bright sky because of the stars, and probably just a bright haze of stars that would really make the... It
just sounds like bright. Sleepless nights to me. But
well, that's right. You need your eye mask, yeah.
And a final question from Candice. In our search for Earth-like planets, is there a limit in the galaxy where we can say there's no point looking at the stars? And she sort of alludes to sort of the closer you get to galactic centre, it gets less and less likely.
It's more suspect astrobiologists would like to look for planets anywhere. What you're faced with is the difficulty. And, when you think of it, the stars that we know have planets are all within about 1,500 light years of our solar system, something like that. Whereas the galaxy is 100,000 light years in diameter, maybe more. So we're only sampling a tiny, tiny fraction of the galaxy, which sensible thing to do. It would be much harder because simply the technical difficulties get higher and higher as you look at fainter and fainter stars. So you're limited by our equipment to only see things within that distance. But it's also where you're most likely to find them, because galactic suburbs are a relatively quiet and peaceful place in terms of horrible things happening, radiation and stuff like that. So it's it's probably and collisions. It's probably a good place to be looking anyway.
Yeah, fair enough. All right, Candice, thanks for your questions. All very exciting. Candice goes on to say, "Thanks for the entertainment. I'm probably too old to be wondering about such fanciful things, but there's nothing worth watching on TV."
I love it. Thanks, Candice. And let me assure you, from personal experience, you're never too old.
never too old. Don't stop. Keeps this thing working.
Keeps it working.
Keeps it going.
Absolutely.
Yes. That just about wraps it up for another week, Fred. Just a reminder to people, if you do have questions for us, and yes, please send some in because I've lost them all. You can do that via our website, spacenutspodcast.com or spacenuts.io. Click on the AMA link to send us your text question or your audio question, or you can click on the button on the right, send us your voice question. If you've got a device with a microphone, you're all set. And it's as easy as just telling us who you are and what your question is. And tell us where you're from as well if we can't pick up the accent. Don't forget, if you want to become a patron, there's information on the website about that. We do occasionally get people saying, how do I sort of contribute to the show? You can do that through Patreon or Supercast, or just through buying us a cup of coffee. That's an option. We're on social media. We're on Twitter. We're on TikTok. We're on Facebook. We're on Instagram. So look us up there and follow us. And don't forget to leave reviews. We love your reviews. We've been getting quite a few really nice ones lately. 1.5 stars. I think it was really good, that one. Yes, please, through your podcast platform, if you're able to give reviews, you can do that. And you can do it on Spotify now. And last but not least, don't forget about our new podcast, Astronomy Daily, where we talk day-to-day astronomy and space science news, which you can find on the same website, spacenuts.io. I think that's everything. Fred, thank you so much. Always good to chat.
Indeed. And some great questions, and lovely to get your mind around them.
Yes, indeed. All right. Thanks, Fred. We'll catch you next week.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large. And thanks to Hugh back in the studio, who's been very quiet today. He must be trying to solve a Rubik's Cube. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.